Section 1.8 covers higher order derivatives. All right, so if you have a function f of x is equal to 2x to the 8th. And then if you, often we use the notation y equals f of x. So if you want to take the derivative, we say y prime, or we could call it dy dx, which is also f prime of x. And if I want to calculate the derivative, I just take 8 times 2, that's 16, subtract 1 from 8, and that will be 7. Okay? This is called the first derivative. So far, that's all we've talked about is first derivative. But there are higher order derivatives. So the second order derivative or second derivative, we would write this just means you're going to take the derivative of the derivative. So here's my derivative, y prime equals 16x to the 7th. So y double prime, or if you will, d squared y dx squared, or you could write it f double prime of x. You just take the derivative of the derivative. So here's the derivative, the first derivative. To get the second derivative, I take the derivative of this. 7 times 16 is 112, and then I subtract 1 from the 7, and I get x to the 6th. So 112 x to the 6th. This is the second derivative. And you can keep going on like this. Okay, you can have a third derivative. That just means the third derivative is just the derivative of the second. Okay. So every time you take a derivative, you have the next one, right? And you can basically, you can go all the way up to whatever number you want. So dn, dy, dx, and is the derivative of the nth order. Which is the derivative of the n-1th derivative. Okay? So most of the problems in your homework are just asking for the second derivative. And then there's one problem, I think, that asks you for the 5th derivative. So you have to take the derivative 5 times. But it's pretty easy. I'll do an example like that. And then there are a few application problems. So let me do another example. This is actually similar to a homework problem that you have. We have x squared plus 6 raised to the 6th power. So we're going to need to apply the chain rule because this is a composition. X squared plus 6 is the inside function raised to the 6th power. So we're going to use the extended power rule. So when we take the first derivative, y prime, we take the power out front, 6 times x squared plus 6, subtract 1 from the 6, and then because the extended power rule here, we have to take the derivative of what's inside. So we're going to multiply by 2x, because the derivative of x squared plus 6 is 2x. And so the first derivative is 12x times x squared plus 6 to the 5th power. Now, to find the second derivative, we take the derivative of this. Notice we're going to have to not only use the chain rule here, but we're going to use the product rule because we have a function 12x multiplied by another function. So taking the second derivative, or finding the second derivative now, and using the product rule. Remember, the product rule is the first function times the derivative of the second plus the second function times the derivative of the first. So here's the first function. The derivative of this is 5 times x squared plus 6 to the 4th power, and then applying the chain rule, we multiplied by the derivative of what's inside. Okay, then we add to that the second function times the derivative of this. Well, this is just 12. The derivative of 12x is 12. So we're going to multiply by 12. And so we have that the second derivative, 2 times 5 is 10, times 12 is 120, and then we have x squared. And then we have multiplied by x squared plus 6 to the 4th power. And now we're adding to that 12x squared plus 6 to the 5th power. So here's the second derivative. Any questions on that? All right. Nothing in the chat box. Okay. Now, as I said, there was a problem in your homework where you had to calculate the 5th order derivative. And a lot of times what you'll see is they'll use, for the notation, they will use Roman numerals. So let me show you, because if you think about it, this looks like a Roman numeral 1. This looks like a Roman numeral 2. So let me do another example. We want to find the 5th order. See, I use a V for the 5th order, and that's also written as d5y dx to the 5th. So when you see this power here on this notation, this just means the 5th order derivative. So you got to start with the first, okay? Our function is given to us as 3x to the 6th minus 7x cubed plus 4x. So here's my original function. Now, the first derivative, dy dx, is just 6 times 3, that's 18, and then subtract 1 from 6 is x to the 5th. 3 times negative 7 is minus 21, x squared, because I'm subtracting 1 from 3. And here's my linear term, so the derivative is 4. Okay, that's the first derivative. Now the second derivative, five times 18 is 90. X to the 4th power, because I subtract 1. 2 times negative 21 will be negative 42x, subtracting 1 from the 2. And the derivative of 4 is 0, so I don't have to write that. Now the third derivative, four times 90 is 360, x cubed. And the derivative of this linear function is minus 42, because that's the constant in front of x. And then the fourth derivative So you will see either one of these types of notation. Again, you just take the derivative of the one that came before it. 3 times 360 is 1080x squared, and the derivative of negative 42 is 0. And then finally, we get to the fifth, whoops, that's supposed to be a v, the fifth order derivative. And it's just 2 times 1080 is going to give you 2160x, because you subtract 1 from the 2. So there is one problem in your homework where you have to actually go and calculate 5 derivatives. And you're just taking the derivative of the one that came before it to get to the next one. So it's pretty simple, not too bad. I'd like to do an example, a simple example. This is another one that's similar to your homework problem. You're given a position of a particle or some position function, and let's see, this will be example 4. So you're given S of t equals 3t plus 9. And since this is a position, when you want to find the velocity, you're going to take v. It's also going to be a function of t. Maybe not, when you take the derivative of this, it's a constant, but so the velocity is just the derivative of the position function. And the derivative of this, because it's linear, is just 3. Now, if you want to find the acceleration of the particle, you take the second derivative, and the derivative of a constant is 0. And then the problem asks you to kind of interpret what your results are showing here. Well, basically what it's showing you, your speed is at a constant, okay? Your speed is constant, or your velocity, but and your acceleration is 0. That means you're not accelerating. Okay, so it's a very simple problem, but I just wanted to mention, what does it mean when you're talking about position? The first derivative refers to the velocity. The second derivative refers to the acceleration. So in another application problem, you are, and I'm sorry if I'm going so fast here, but remember that we lost Monday because of the holidays, so I'm trying to cram 2 sections into one day. So apologize for that. But if you have a population, so a deer population is modeled by a function p of t is equal to 2000t divided by 4t plus 75. So this is another problem from your homework. The numbers might be a little different, but I think the function is the same that you're working with. And you're asked to calculate the derivative of your deer population. So if you calculate the derivative, notice this is a quotient function, so we need to use the quotient rule. So the derivative is the bottom function times the derivative of the top. Derivative of 2000t is just 2000, minus the top function, 2000t, times the derivative of the bottom. The derivative of 4t plus 75 is just 4. This is a linear. all divided by the bottom function squared. Okay, that's the quotient rule. And so to simplify that, notice that, let's see, let's go ahead and distribute this. You'll get 8,000t. And 2,000 times 75 is 150,000. And then notice here we have minus 8,000t, because 4 times 2,000 is negative 8,000t. So the 8,000t minus the 8,000t, those are going to cancel. And that's all divided by the 4t plus 75 squared. And because this section is in the higher order derivative section, 1.8, that's what we're talking about, they want you to calculate the second derivative, which is the derivative now of this. And this simplifies as 150 over 4t plus 75 squared. Now, notice I don't have any variables in the numerator, so when I take the second derivative, I'm going to first write this as, I'm going to write the first derivative as 150,000, that's my numerator, multiplied by 4t plus 75 to the negative 2, okay? I want it written like this because now I can apply the power rule and of course the chain rule with it, the extended power rule, because I have a composition here. So when I'm looking for the second derivative, as the problem asks me to find the second derivative, I take a negative 2 times 150, and let me make sure I did this right, because I've got a different answer in my text, in my notes here. I may have made a mistake in my notes. Let me see here. Just give me a second. Hold on. Somewhere I've got a negative 2 in there. I don't know where that came from. Oh, okay. Oh, I know what it is. Okay, never mind. Sorry. All right, so we have negative 2. Now I'm taking the derivative of this first derivative. And like I said, I want it in this form because I can just apply the extended power rule. I take the negative 2 times the 150,000. And then, of course, I'm subtracting 1. So I get negative 2 minus 1 is negative 3. And then by the chain rule, I have to multiply by the derivative of what's inside. So that is going to be, I always like to use my red to highlight that so you don't forget it, times 4. That's the, let me just write this. Okay. And this works out to, simplifies to, so we have negative 2 times, well, 15, let's say, that's going to be 30 plus 4 zeros, and negative 30, and then you got the 4, so that's going to be negative 120 plus 4 zeros. So that's going to be 1,200,000. And then, of course, you have the 4t plus 75. And this negative, just that's why I put in the denominator, because of that negative. All right, so this is my second derivative. So let's talk about what these are telling us. So here's the original function. And over time, as you go forward in time, notice that the first derivative is positive because we're squaring. Here's the first derivative. We're squaring it, and this, so that's going to, the denominator is positive, the numerator is positive. this whole thing is positive. That means that the rate of change for your population of deer is increasing because this is a positive number. So the population is growing. But if you look at the acceleration, which is the second derivative, it's negative. This denominator is positive because time is positive. You go forward in time, it's positive, and you cube it, it's still positive, but the numerator is negative. So this whole thing is negative. So it's decelerating. Okay? The population is decelerating. So it doesn't mean that the population is decreasing, right? We know the population is increasing because the first derivative is positive, but the rate at which it's increasing is going down. So there's going to be, it's getting less and less and less. So as time goes forward, imagine going off to infinity. If you could imagine time going off to infinity. Let's say the limit as t approaches infinity of our population of P of t. Well, remember for high values of your function values, remember the 75 becomes, the 75 becomes inconsequential when you compare it to these two powers. So this is going to actually be the same as 2000t over 4t, and if you simplify this, the limit is 500. So the population, and I don't know, it's probably not 500 deer, well maybe it is. It might be in thousands or something. I can't remember what the problem said. I don't think I wrote that down. You know, sometimes the model of the population might be in thousands or 10,000s or something like that. But anyway, the limit of the population is 500. It's never going to get more than 500. It's always increasing as you go forward in time. That's because the first derivative is positive. But the rate at which it's increasing, that's the second derivative, is declining. So it's decelerating, but the population is still increasing, if that makes any sense. So 500 is kind of the limit on that population. So it's an interesting application. Any questions on that? That's how we interpret changes in your function, and then also the changes in the changes, which is your second derivative. So that's the interpretation, and it's kind of interesting. Anyway, you're ready now to do your homework for section 1.8, and then on Monday we will review. So the test will be due Thursday at 11:59, so be thinking about that. And the best way to study is to practice the quizzes, because those are the most like the tests. Okay? Any questions before we sign off here? So we're done a little bit early, but anyway, you have a good rest of your week, and we'll see you on Monday.